Okay, moving on then. I'm not going to try and race through too much, to be honest, and I'm not expecting to get through the whole of the section on the eye when we get to that, and even if it means finishing early, I want to save some of it to finish in the week when we come back after Christmas, so that we've got something to focus on, really, to draw together what we have been doing. Right, so we did reflexes, we did the autonomic nervous system. I forgot about temperature control, so that's just going to be a quickie, really. It's an example of a homeostatic mechanism that involves the nervous system. We've done several homeostatic mechanisms that involve hormones. I talked about ADH and osmoregulation, and talked about blood glucose control through insulin and glucagon. Sort of left it at that, I suppose, and loads of others we could have done. With the nervous system, it just needs an example, and so we'll do temperature regulation just in a fairly superficial way. It's not very complex. And you've got a double-sided sheet that summarises it. Now, the thing about humans is, of course, we are mammals. Mammals and birds have something in common in the way that we describe them in terms of their body temperature. They are endothermic. That wasn't what I was expecting you to say. Warm-blooded, yeah? Any other animal is cold-blooded or ectothermic. The endo means inside, so we're generating our own heat inside. Ecto, therefore, would mean outside. So ectothermic animals have to get their heat from the environment. So calling them warm-blooded or cold-blooded is rubbish, really, because if they live in a cold climate, they will be quite cold. If they live in a warm climate, they'll be quite warm. And, you might have seen the wildlife programs with the lizards and things that come out and bask on the rocks in the sun before they can actually get going for the day. We maintain a constant body temperature. So no, our body temperature doesn't vary at all, or it shouldn't. If it does, we make huge efforts to put it right. That's really what this is about. And it's the same with all birds and mammals. And because we have one of the mechanisms for keeping warm is fur and feathers, isn't it? I mean, our fur isn't up to much as far as keeping us warm is concerned. I mean, my head's fine, but But we go to a lot of hair removal. And somebody yesterday was talking about someone they knew who had alopecia and someone else who'd had chemo and lost body hair and actually felt the cold a lot more. So even though we tend not to think of our hair as being particularly good as an insulator, we're not noticeably furry, most of us, it does contribute. Sorry? We do, yes, absolutely, yes, yeah. With the loss of body fat with anorexia would encourage the body to grow more hair to keep warm. So yes, there's a sort of tipping point, if you like, and I mean, hair's part of it. Fat is something that we haven't. Well, I will say we don't have control over. It is. It does seem ridiculous, doesn't it, that fat is actually more involved perhaps with hibernation and perhaps getting through the winter months when there might not be much food available. So how come, it's another one of the arguments against evolution in a way. How come we've evolved to still store fat so efficiently? Because it's actually a greater threat to our health. And the fat is used particularly, but, excess fat, we are still able to store excess fat, even though it is more likely to damage our health than it is to help us survive. It actually reduces our life expectancy rather than increase it overall, doesn't it? So, in terms of evolution, we have made a few mistakes along the way, I think. Evolution isn't infallible. And, sorry? Well, yeah, people's weight does fluctuate. It will just be due to it's energy in, energy out, isn't it? In the winter we tend to eat more just to, there's a comfort side to it, and it might only be that you think, oh well, I'll have a hot drink to warm myself up a bit, But what do you have with the hot drink? You know, you might have a couple of biscuits or something like that, and then it's likely to perhaps be bigger meals, and you know, whenever you have your bigger meal. And then in the summer, you are outside, out and about more, perhaps more active. So yeah, the balance is not unusual. It's not unusual at all. There's also the I was talking about seasonal affective disorder, wasn't I? And if you have particularly high levels of melatonin in the winter, that can actually increase the weight that you put on. So, you know, so yeah, it is just a sort of, there should be another one of those responses like flight and fight, rest and digest, store and snore or something like that. You know, it's sort of, yeah, put the fat on and go to sleep. You know, I would love to hibernate. Don't know about you. Particularly this year with having no heating the last few weeks. It's been... Well, you'd have to move it about. When my kids were small, there was our Christmas film used to be, and now this shows my age, but I don't know if any of you are familiar with the cartoon called Yogi Bear. Yeah, Yogi Bear. Yogi's First Christmas was our, it was our sort of kids' Christmas. We would always put it on while we're putting the decorations and things up. But Yogi's First Christmas is based on the fact that, yes, bears normally hibernate over the winter. But for some reason, I can't remember what it was, Yogi Bear had actually woken up and he was awake, and this was his first Christmas because he'd normally hibernate. So, oh, picnic basket, yeah. Anyway, moving on, instead of confusing whoever might be listening to the recording of this. Yeah. Complete with ramblings, nearly 7 minutes in. Right, a little bit about temperature control. So we're very good at it. And we have to maintain our body temperature quite narrowly, don't we? You know, we haven't got much room for fluctuation. And, you know, if you are going into healthcare, then one of the first things you do with a patient, take their temperature. Because it will tell you if they've got an infection usually, because that creates a fever, doesn't it? So if the temperature is up a bit, it will tell you there's potentially an infection. It's also useful, you know, if you've got someone who's come in, perhaps off the streets and it seems to be unconscious, you can check body temperature for hypothermia, can't you? And hypothermia kicks in, can you remember? 35. Yeah, 35 is the tipping point for hypothermia, which is, it's not much leeway there, is it? That's your internal temperature. It's not your skin. Your skin can be absolutely icy, but you're still maintaining a normal temperature. So your skin is never a very good indicator of your internal temperature at all. And particularly, without putting too fine a point on it really, the fatter you are, the colder your skin's likely to be. So my skin can be incredibly cold sometimes, but inside, normal temperature. Because obviously the fat provides an insulation between the internal and the outer layer. So, yeah, I don't pay attention to my skin temperature at all. That might be absolutely freezing, but as long as I'm not shivering, I'm all right. Now, this is one of those systems where we've got two different sets of control mechanism. But how does our body then keep an eye on our temperature? What's it actually using? Well, yeah, before that, before shivering, how does the body actually check your temperature? Huh? No, not responses. I don't want responses to high or low temperature. Which part of your body do you think detects your temperature? Your brain, yes. Yesterday, we had the hypothalamus, got a brief mention, didn't it? And it's sort of got a thermostat in it. And as your blood goes through, it checks your core temperature. All right, so blood temperature is what we're really looking for. Right, temperature control. We have what's called a thermoregulatory centre. That's in the hypothalamus. And that monitors the temperature of the blood as it passes through. So we've got two possibilities. We're either overheating or we are chilling, and so we need two ways of correcting this. So if our body temperature goes up, so increased temperature, what do we get? Well, we've got to hang on, rather than a colon there, I'm just trying to think the best. I want the quickest way of writing this. What we get are heat loss mechanisms. So ways in which we can lose heat. How can we lose heat? We can produce sweat. Now sweat alone is no use, because what's the temperature of sweat? Yeah, well, it's body temp 37, isn't it? So that in itself won't cool you down, will it? It's got to be able to evaporate. If your skin is wet, the sweat won't cool you down. You actually have to, you know, if you're exercising and you get really hot and sweaty, you need to towel that off so there's damp layer on the skin. That then evaporates and cools you off. All right, so it's evaporation of sweat. Takes a lot of energy to turn the water in sweat into water vapour. What else will help us lose heat, do you think? Wrong way round. Come. What about the skin? What might happen to that if you're really hot? Goes red, yeah. So if you divert more blood to your skin, it'll radiate the heat away. Yeah? There's something else in the skin that's associated with temperature control that I've been talking about. It's the hairs, isn't it? What do they do if we're hot? Well, yeah, they're going to lie down flat, aren't they? So hairs lie flat. We put most of our efforts though into sweat production, because that is very efficient, because it's over the whole body, and the evaporation of sweat uses so much heat from the body. And the opposite diversion then, or deviation perhaps, what we're going to need, well, this is going to require heat conservation. I didn't really need to write mechanisms out again. So, how are we going to keep heat in the body? Well, we could use some of these. Are we going to keep sweating? So we'll, hang on, reduce sweat. And then, yes, last, Danny, we can have shivering. All right, we can put the shivering in now. Shivering is that completely involuntary muscle contraction. I don't know if anybody's ever shivered properly, where you literally cannot stop yourself. And yes, actually, yeah, with a fever, you get that really bizarre situation where you're hot but you're shivering because your thermostat's been reset. You know, it's like when somebody sneaks past and turns it up. And it's like somebody's sneaked past, turned yours up to 40. So you're really hot, but you're shivering to create more heat because somebody's reset your thermostat. And that's what the infectious organisms do. Why? We don't know. Whether they do it because they prefer a warmer environment, or whether the body does it trying to get rid of them, nobody really understands the sort of mechanism there. But how it gets reset, you know, we just know it happens. We don't know quite why. But this thing, you know, with an infection, is the presence of the organisms in the body that triggers this, isn't it? And yeah, so your body goes all out trying to make more heat, more heat, more heat, so it shivers away, and your temperature's going up, and that feels just so bizarre, doesn't it? You know, that you're hot but shivering. And then when the fever breaks, of course, what happens then? well, you sweat for England, you know, you're just pouring sweat. That cools your body back down to normal. But then you sometimes find you go back again, you know, you can go through cycles of fever with it. So you alternate between shivering and sweating. So the sweating should bring you back down to normal, but if you've still got the infection, then that can trigger it all off again. So you start shivering again, heating up again. And yeah, it's controlling the temperature, of course, is the key with fevers, isn't it? So shivering is that involuntary muscle contraction that generates heat, and we know that muscle contraction generates heat. Right, what else could we do then? Yes, so what are goosebumps? Well, well, what's trying to happen? It's hair follicles, isn't it? The hairs are trying to stand up, but they're limited use. Although, as I said yesterday when we were talking about people with alopecia or after chemo, that it did make a difference. But I think the use for us is perhaps more that it alerts us, doesn't it, to being cold, and it's sort of saying to us, you know, oh, you know, put your jacket on, or turn the heating up, or get indoors, or something like that. And I think that's the main use for us, really, because it doesn't really, it's not the same, is it, as with furry animals and birds that can fluff themselves out. You know, I haven't seen many people capable of fluffing themselves out to an extent that would keep them warm, but it does help us a little bit. So hairs stand up. The idea is to try and trap a layer of air against the skin, a bit like wrapping yourself in a duvet or something like that, so something sort of puffed out. But the effects are minimal, probably. And then the other bit up there, of course, and we probably have experienced that in the last few days this week, blood doesn't go to the skin when you're cold, does it? Yeah, it goes to your organs. I mean, your fingers are usually the first place, aren't they, that start to go pale, then they go white, toes as well, yeah. Then they go blue, then they go black and drop off, yeah. So blood diverted away from the skin. Yeah, you can ask away. Ask away.
When we're talking about like temperature going up,
Yeah,
like,
temperature.
in relation to hormones, like
Oh right, yeah,
stuff,
yeah.
Like,
Menopausal temperature fluctuations are. I'm not sure that anybody knows why menopausal hormone changes cause that. I mean, why would changes in estrogen have anything at all to do with temperature? But they do, in a way, reproductive hormones, because if you think about the ways in which you can actually predict your fertile days in the month, you do it with temperature. Yeah, so there clearly is some sort of link between temperature and hormones, but it just goes, it just, yeah. Yeah. I mean, the hormonal changes are just bizarre. And then, of course, you know, your temperature goes up, and then it's the hot flushes and the sweating, and yeah. And yes, it can pursue people for years or hardly at all. But it's something to do with estrogen. But I don't think anybody's very clear. Yeah, yeah. Yeah, there is definitely a link. There's definitely a link between reproductive hormones and temperature, but it doesn't make sense, if you like. And yeah, I mean, if people go on to hormone replacement therapy, then that will control the hot flushes, or take other forms of estrogen, like plant estrogens, soya, that sort of thing, can actually reduce them. But you know, the reasons are, yeah, very difficult to explain. So. Yeah, it just, I mean, we're looking here at the nervous system and how that controls temperature. So where hormones actually think they've got a right to get in there, I have no idea, because it must be the effect of hormones on the brain, because the flushes and everything happen really quickly. You know, in terms of the way that estrogen normally works, of course, we're talking days and weeks and possibly months, aren't we, as to how estrogen cycles round, it comes and it goes. And yet, you know, take it away, and then all of a sudden in a process of seconds, you know, the body can be an inferno and sweating for, you know, some sort of prize. And then it resets itself to normal, and yeah, it's gone, it's passed. And, you know, there's no sort of tally with the way that hormones normally work there. It is very much as though the hormones affect the nervous system and just they must, you know, fluctuating levels must kick the thermoregulatory centre somehow. So, no idea, but oh, if you, yes, overheating, it's sort of like heat stroke sort of effect, yeah, yeah. Oh, right. So, collapsing in Primark is not something you want to do. And again, you know, anyone listening to this is not going to pick up your voices, so they will have no idea what I'm talking about. Ha, ha, ha. Oh, dear. Right, that's all I'm going to do on the temperature control thing. But we are now going to switch on to the eye. Now, all of this, I'm not doing any written notes on this. All of this is on a PowerPoint. And you have it printed in your folders, along with a few additional diagrams that we'll come back to, structural diagrams. And looking about on the bench, we have a model eye. So I can now remove the brain. Again, that's going to sound very strange, isn't it? Remove the brain, replace it with an eye. I need to do some tidying up here. Okay. Eyes. Interesting things, eyes. The timing of what I do on the eye is a little bit hit and miss at the moment, because I only started doing it on the course from last year. I'd never taught the eye on Access. We used to have it on A level, and then obviously that finished a long, long time ago. But year before last, we were up for revalidating the Access course. And because we write our own course, all these units have been written by us, and we can decide what goes in them and what we assess. All right, Carver basically just says, yep, that's fine, or no, you need to rewrite that bit. But I decided it would be nice to have something different in this particular unit. And consequently, I've introduced the eye and the kidney, neither of which I've taught for a long, long time. And it's just nice to have a bit of variety sometimes. So the timing is not quite sort of settled yet, because it's only my second year of having it in the course. So my ramblings are not quite as predictable. So I could end up in all sorts of places, or I might shoot through it so fast, you know, wonder why. Eyes are, let me just save that and get rid of it. They are quite useful, yes, yes. Good point. Extremely useful. And in addition to that, we have two. There's another comment for you. So that might, yeah, just one would not be as efficient. It would be enough. Yes, interestingly. You can. Yeah, the bizarre thing is, yeah, you're allowed to drive with one eye. I know this. I know. I know this because many years ago, Mum had cataract operations, and they only do one eye at a time with those, for obvious reasons. And we checked it out, and you're allowed to drive with one functioning eye. Well, you turn your head, don't you? You know, your visual field is actually quite, yeah. I mean, and yes, we all have. There's a limit, but you know, by actually moving your head, it's, yeah, yeah. Whether it's changed since then, I don't know, but yeah, that's quite a long time ago. I must say, we're talking about probably 15 years ago, but you could drive with one eye at that time. Now, the issue is not so much the being able to see, you know, the range of your visual field, because it doesn't take much just to move your head to sort of see those bits. It's actually more to do with shape and speed. it's really hard to judge speed of things coming towards you with one eye. Because we have, yeah, thank you. Yes, you can drive with one eye. There you go. Oh, we love Google. But if you've got two eyes, you are getting a slightly different view of things, aren't you, from each eye? It's what we call stereoscopic vision. Stereo meaning shape. So it gives you that perception of shape, and movement is part of that, isn't it, really? And it, you know, that if you can see both sides of something coming towards you, you get, you know, an impression of its speed. So with one eye, that's much, much harder. An actual position, you know, if you close one eye and try and pick something up, it is just a little bit harder to do that. You know, to, you know, even just to pick something up, you will realise that actually you don't get quite such good information into your brain. So having two eyes is really important, and you know, we can manage with one. It's not just a redundancy thing, you know, spare, as it seems to be with some organs, but you've got yeah, purpose to these two eyes. Now, our eyes are positioned in the same way as predators' eyes, so on the front of our head, so it does suggest that, you know, we are predators. We do hunt prey, which sort of tallies with, you know, our origins, doesn't it? So if you think about hunting animals, you know, cats and birds of prey, and, you know, their eyes are on the front. Whereas animals that are prey animals, so perhaps rabbits and so on, tend to have eyes more on the side of their head, so they actually get better vision almost all the way round. They can almost see round their entire bodies. I can't imagine what that must be like. There is a bird I remember once reading about that can actually see better behind it than it can in front. It's got more overlap between its eyes behind it. But then again, you know, if you're being approached from behind because the predator thinks, oh, I'll sneak up on it from behind, quite helpful to be able to see well behind you, isn't it? But the yeah, the position of them just suggests that we've come from a predatory background. And what we're going to do is to just start off by looking at the structure. So it's, you know, we're not going to look at how they work. It's a bit complicated, and at this point in the term, you know, I can barely handle it, so, you know, I'm not going to go into huge detail. Right, our model eye is not hugely helpful, but the eye is protected by the bony socket that it's in. It's held in by ligaments, but it also has 3 pairs of muscles arranged around it. You've got a pair top and bottom that allow your eyes to go up and down, a pair side to side that let your eyes go side to side, and then a diagonal pair that just sort of coordinate and allow you to, yeah, do everything else. And some people can do some very strange things with their eyes and actually move them independently of each other as well, which is strange, isn't it? With those muscles, if the muscles are slightly longer than they should be, you get the condition known as squint. All right, squint is where at least one of the eyes is pulled further in than the other, or, well, you could have it in both eyes, actually. Sorry? Lazy eye, yes, is when that happens sort of some of the time. And, yeah, well, have they... Usually with children, if it's a significantly lazy eye, they will give you an eye patch to cover the other eye.
He's just got glasses.
All right. Okay, yeah. That's now that's an interesting thing you say. That so it's actually a genetic thing, isn't it? I think because yeah, my husband had a proper squint and actually had it operated on. And they were looking very carefully at our sons when they were born to see if they developed it, which they haven't. But yeah, you can actually shorten the muscle that's you know, that causing the imbalance, and you know, just pop the eye out, shorten the muscle, pop it back in again. It's funny, you know, out of all the things we talk about, talking about eye surgery is the one thing that makes most people cringe. And we were talking about, because I mentioned cataracts. Of course, cataract surgery, you're wide awake when they do this. And it's like laser surgery on the eyes, isn't it? You know, you're awake. But for cataract surgery, they cut into your eye, they break up the lens and take it out, and then replace it with a plastic one. And yeah, and it's an interesting operation, but you know, you are awake. You can't really see because they're so close and they dilate your pupils so much. But eye surgery... Huh? Yes, yes, you'll have local anaesthetic drops in your eye, and yeah. Well, they might. It might be an injection. You know, it's perfectly possible. But it's you'd probably have anaesthetic drops, then an injection, I should think. But I don't know. I'm just waiting for it to come round, and then I'll let you know. And a lot of people, you know, somebody yesterday said, oh, if I get cataracts, they're staying there. I'm not having that done. But there are benefits to it. If you've got other sight issues, like long sight or short sight, when they take the cloudy lens out with the cataract and replace it with a plastic one, that plastic one can correct your vision. And it's almost an option for vision correction instead of glasses or contact lenses, is you could have your lens replaced in your eye. The only thing it doesn't correct is the age-related needing reading glasses. But when Mum had hers done, whenever it was, let's say 15 years ago, she was quite short-sighted beforehand. But once she'd had the cataracts done, she didn't need to wear her glasses apart from reading. So, you know, I'm thinking, you know, there is a hidden bonus there, because my eyesight is very poor. I've got very, very short sight. And so, yeah, I've even investigated the potential for getting lenses replaced, you know, instead of wearing glasses and contact lenses. So yeah, eye surgery is the one that makes people, yeah. Right, let's have a look at what we've got here then. Gone are the days when we used to dissect eyes. There's no point, because you jab your scalpel into it, it goes splat, that's it. Yeah, they never really achieved anything. And we used to use bullseyes, and we had to stop doing it. And this was when I was teaching in schools, I think, because of BSE. Because obviously a bullseye has got the optic nerve that comes out of the brain. So you can't have any, you know, cattle nervous tissue. You've got several layers here that we need to talk through. So first of all, on the outside is this tough white layer called the sclera. It just holds the eye in shape, really. You need a certain amount of pressure in there, but one of the problems you can get with eyes is a build-up of pressure, which can actually damage the retina, and that's a condition called, that one's glaucoma. Yeah, heard of glaucoma? Glaucoma is inherited, and if you have a close relation, it's got to be a close relation, a sibling or a parent, then they will do the full test. But they usually do an initial pressure test on most people when they have an eye test, which is the air puff. Yeah, well, that air puff checks the pressure in your eye, and if that threw something up, then they do the sort of full test for glaucoma. I had an aunt with it who went blind as a result, but she's not a close enough relation for me to be properly tested for it, but they checked me anyway. So you've got the sclera on the outside, really tough, really protective. And then inside that, you have a layer called the choroid, which is pigmented. It's got a black pigment in it that stops light reflecting inside the eye, so it doesn't just bounce about. It just stays in one place, it absorbs the light. Now, if you go to the front of the eye in relation to these bits, you actually have the window, which is called the cornea. The cornea is the bit that does most of the focusing. So when they do the laser surgery, it's on the cornea, and they just sort of skim a bit off it, you know, sort of file it down, sand it down with a laser. Because that's the bit that does most of the work in focusing the light in the eye. People think it must be the lens, but actually it's not, it's the cornea. So you can actually, you know, reduce that or reshape it to deal with astigmatism, and yeah, correct vision that way, as long as your eyes aren't too bad. Mine are too bad for laser surgery. So we've got the sclera on the outside, the choroid inside that with its pigment. We've got the cornea at the front. There's a lot of bits in here, aren't there? Then inside the eye, the light-sensitive layer is the retina. That's the yellow bit on this diagram, which obviously you haven't got in colour. And the retina contains two sorts of cells, rods and cones, and we're going to talk about those a lot, but probably not today. I can't see me getting up to that. The retina has got a particularly sensitive area called the macula, part of which is the fovea, which is where we concentrate the light if we're, you know, really looking hard at something. Macular degeneration, yeah, that's a common cause of blindness, isn't it? Well, it creates like a spot in the middle, and you can see why now. That's right, yeah, so you sort of have to look to one side to make it fall on another part of the retina. You also have part of the retina where there aren't any light-sensitive cells, and this is where the optic nerve leaves the eye. So if there aren't any light-sensitive cells, what should we call that? You'll know it when I say it. It's the blind spot. Right? There is literally a blind spot in each eye. Now you can prove it's there. If you take a piece of paper, I've written all over this one, and you just put a spot and a cross about 10 centimetres apart. I will show you. Right, about half a centimetre in size. All right, I'm going to walk round with it so you can see. Because I shall just, if you all right, so about 10 centimetres apart, a spot and a cross, and like that. All right, so if you put those on a bit of paper, and then you hold the paper, get back within range of the thing. Once you've done that, you then hold it at arm's length, and you close one eye. I would suggest the one on sort of on the other side. And you bring it towards you, but you have to concentrate really, really, really hard on one of the shapes, and there will be a point at which the other one disappears. And it's really quite, it's always it's quite creepy, isn't it? All right, so if you hold it there, you have to change the position a bit sometimes, but you bring it in, and yeah, I've lost the cross. It's disappeared by but you can then look across to it, and it's there, and then you look back away from it, and it's gone. You need to sort of hold the paper to one side, I think, rather than very centrally. So, yeah. But interestingly, what do you see in that? What does your brain tell you that you see? It says the paper's still there, doesn't it? You know, it's not some sort of black, sort of nothing. Your brain fills it in. But you can trick your eyes, can't you? Now, I forgot to mention this one when I was talking about it yesterday, but I've got a lot of optical illusions on the end of my PowerPoint. But of course, one of the classic ones was the dress, wasn't it? Do you remember the blue, black, or white, gold dress on the internet? Yeah, I gather it was blue and black. Oh, gold. Gold? No, sorry, blue and black, gold and white. I could not see it as blue and black.
No, there was one.
But there's, yeah, the way that our eyes interpret information coming in is very, very variable. And you can trick your eyes. And it's, you know, hours of entertainment with these things. Right, so that's the blind spot. Anyway. It's all right, but you made it work, yeah? Yeah, it's creepy, isn't it, that it just disappears. The rest of the eye, if we quickly go through this, and then you can find somewhere to go to sleep. We've got the back of the eye is filled with a sort of jelly. It's called the vitreous humour. Now, the word humour goes back to sort of history of medicine, that they talked about the 4 humours of the body. I think it was blood, yellow bile, black bile, and phlegm, or something like that. But we're talking sort of, I don't know if we're talking medieval or when. But it was, the illness was about imbalances between the humours. So humour basically just means stuff. And this is the vitreous humour. All right. Now, it's a clear jelly. Now, vitreous then, what does vitreous mean? Well, you actually do, you will be familiar with the word in a slightly different form, but you won't necessarily know what it means. What's another word for creating a test tube baby? IVF. Right. Now, what does that stand for? No. Yeah, well spotted, yes. There was the V that was supposed to give you the hint that it was like vitreous, but it's not. It's in vitro. Yeah, in vitro fertilization. Now, what that actually means is glass. So this is a glassy humour. It's clear and lets light through. In vitro fertilization is fertilization in glass, a dish or a test tube. Yeah? What's the other option? If it's not in vitro, it's in vivo. In vivo, in life. Yeah? So either in a glass dish in vitro or in life is in vivo. So, yeah, oh, uvavu, yeah. In vivo. It's sort of, yeah. Well, in vivo is natural fertilization, shall we say, and then in vitro would be in a dish, in a glass dish to be precise, you know, not plastic, not China, it's got to be in glass. So this is the vitreous humour. This helps to, well, it supports the eye and it helps to focus the light. And then we've got a lot of stuff happening at the front. So, what do we got at the front? Well, behind the cornea, there is the aqueous humour, so that's watery, that's more stuff, and that's the watery bit. You then have a couple of more very important sphincters. So, you see, today's word is sphincter. So you've got 2 in each eye. So there we go, 4 sphincters in your eyes. And we've got one that forms the coloured bit of your eye. The coloured bit's called the iris, and it's a sphincter. S-P-H-I-N-C-T-E-R. So the iris is a sphincter muscle, and if it contracts, it closes up the pupil. If it relaxes, it opens the pupil, so it constricts and dilates. The other sphincter goes around the outside of the lens. Now, this is sort of misleading because it's very two-dimensional. The lens is actually, I've lost it. Oh, no, there it is. You know, it's a three-dimensional thing, but it's held in a sort of ligament-based bag, which is then pulled by another sphincter muscle called the ciliary muscle. And if that contracts, it lets go of the lens and lets it go squishy and fat. If it relaxes that sphincter muscle, it'll get bigger and it pulls on the lens and makes it thin and flat. And that's how we focus on things. That's how we change our focus. You know, there's a difference between looking here and looking in the distance. And, you know, you can't see near and far away at the same time. But if you've got, you know, a lens that you can change the shape of, then you can change the focus. So you've got the next few slides sort of take us through some of these, but I will probably recap this anyway. I'm just going to do a quick skim through. So we start off with the iris is the coloured bit, and it's this muscle, a sphincter to be precise, that controls the amount of light entering the pupil, which is the hole. We've then got the sclera, which is the white bit that you can see around the outside of the iris, supports the eyeball and allows the muscles to be attached. The lens, actually the lens is a really weird thing because it's made of cells, but it's clear and crystalline. So how does that work? Did look it up once, can't remember what I found out. That's because it's a long time since I've taught the eye. I could look it up again, I suppose. And this is what allows us to focus on near and distant objects. We've got the cornea over the front. That's a rather bizarre sort of three-quarter diagram showing you the cornea, the iris with the pupil in it, and then the lens behind that. And the cornea does most of the refraction of the light, which is what causes the focusing. And then the retina is really sort of where we need to concentrate our efforts because that's the bit that actually detects the light. So we'll just have an introduction to this and then we will leave it till after Christmas. So it's the internal surface of the eye. You've got these two sorts of light sensitive cells in there. There are rods and there are cones. And they are responsible for creating nerve impulses out of light. The blind spot doesn't have any of those. Doesn't have rods, doesn't have cones. And usually the other eye will compensate for the blind spot. So that's why you can actually prove it's there by covering one eye. because the rest of the time, you know, your brain's creating an image from both eyes. Now, the optic nerve is something that I only mentioned as being the sort of connection. But the weird thing is, with the optic nerve, it has to get to the brain, and it has to get right to the back. The visual area in the brain is right at the back of the head in the occipital lobe. And the image that our eye actually creates is upside down and back to front. I don't know if you're familiar with the idea that that's what magnifying glasses do. It's the nature of that shaped lens is that it, you know, turns the image upside down and back to front. So actually, yeah, our eyes are not sending our brain a particularly good image. You know, the brain would say, well, I can't do anything with that, so it has to flip it over and turn it, you know, the right way up. And although the left side of the body deals with, the left side of the brain deals with the right side of the body and vice versa, with the eyes you get this odd sort of scenario where there are fibres going from each eye to each side of the brain. So it does mean that, you know, you've got a bit of fail-safe in there. So you are getting information from both eyes, crossing over as they go through the brain, but, you know, providing, you know, a more accurate or more reliable sort of image. Now, this is where I want to just get to and then stop, about the rods and the cones. Rods are called rods because that's the shape they are. And there are 120 million of these. I don't know if that's per eye or between the two of them. And all they do is detect light intensity, not colour. They've got absolutely nothing to do with colour. So animals that don't see colour, like cats and dogs, only have these. All right, so not all animals see colour, do they? And colourblind humans, well, they will actually have the cones, but they don't work properly, or different colours of light will actually trigger the same cones. So the use of the cones is low-level light. So at night, we use these. The problem is in bright light, like now, what we say is they get bleached out. They don't work. We're not using our rods at all now, and they've actually got overstimulated. So if you now walk into a dark room, you won't be able to see anything for a while. And then your rods reset themselves, and you start using those, but not the cones. And it's the same if you go out to look at a particular star or a planet or something, that you actually have to go outside and wait for a while, don't you, before before your rods will actually work. And if you turn the light off in your bedroom at night, your immediate response is you can't see anything. But if you wake up in the middle of the night, you can, because your rods have reset themselves. Yeah? You can start to, but yes, but the complete reset for real clarity takes a while. And somebody raised yesterday about pirates. It was one of those days. That there is this theory that pirates wore an eye patch over one eye so that was always ready for the dark, so that they'd be able to see, they could just switch it to the other eye when they went below deck. So whether that's true, I have no idea. But you know, if you're boarding a ship and you want to steal stuff off that ship, you're going to have to go below decks. Chances are, you know, you're not going to be able to see. You'll fall down the stairs. You're going to make a bit of an idiot of yourself. You're not going to see people coming towards you. You're not going to find anything. So yeah, having one eye ready for the dark, actually, yeah, good strategy. So I don't know if that's true. Yeah, it's true. So they could. So there we go. So pirates can see in the dark. Yeah. So there you are. So, see, you'll be able to astound people at the Christmas dinner table. Yeah. Never mind the jokes out of crackers. And there are plenty of pirate jokes about. Quickly, last bit. Males are more likely to be colourblind because one form of it is on the X chromosome. Yeah. The cones, on the other hand, there are three sorts that detect the three primary colours of light: red, blue and green. And we find most of these in the fovea, that bit at the back of the eye that we concentrate on. And although the rods can pick up they're good for sensitivity because they will pick up low levels of light, The cones are there for what we call acuity, which is detail. There aren't that many of them, but they are packed in, particularly to one place. And if you look across the retina, you get this sort of effect. So at the outer parts of the retina, you've got mostly rods, but then when you come to the fovea, you've got this peak of cones and no rods. So that's the bit, when you're concentrating on something, the light falls on the fovea. It would really, yes, yeah. So that will give you colour distinction. So yeah, but it's also interesting going back to looking at stars and planets. If you go out at night, they say that it's really difficult to force yourself to do it. If you are looking for a particular planet, let's say, is you're supposed to look to one side of it, because if you look straight at it in low light, it'll fall on your fovea. You won't be able to see it because it's not intense enough. So look to one side of it, concentrate to the side it's going to fall on the fovea, and then the planet will be imaged on part of the retina, like here, for example, away from the fovea. So, peripheral vision, you tend not to pick up colour so well. If you're looking ahead now, then, round the edges, you're not so aware of colours, are you? But we do a lot of filtering as well. There's something else we were talking about some other time, I can't remember, I don't know if it was it in this group about filtering information? No, it's supposed to be one of the big issues in autism, is the lack of ability to filter. See, most of the time we filter out the vast majority of incoming, don't we? You're now looking at me, but you can see the board, the notices over there. You can see out of the window. You can see things all around you, but you're filtering those out and focusing. Similarly with sound, you can hear me talking, but you're filtering out perhaps the sound of this fan running, the sound of the building works outside, the sound of people in the corridor. You filter those out. But in autism, there is much less ability to filter, so they get overwhelmed by, so hence there's a lot of sort of contracting into a limited space so that there's not so much distraction, in order to function. It's hard to imagine what it must be like, isn't it? To just be aware of everything. Absolutely, everything that's coming in. But I had the student last year that I started recording stuff for. Her sensitivity to sound was horrific. I couldn't click a pen, turn paper. Even people breathing could be a problem some days, but that's probably a bit extreme. But it's a really sort of difficult thing to imagine if if your filtering is okay. Well, she would just use loud music. She would sort of overwhelm, a bit like me wearing the TENS machine to overwhelm the pain signals from the nerves in my back. You can use music in your ears to do that, but obviously that makes it difficult then to communicate with people. So you couldn't come into class and hear me because she'd have the music on. But so yeah, it is, but it's sort of yeah.
Quite a few kids at school with autism are wearing
headphones is part of that, and it's sort of I think there's a degree of being able to learn to manage it, but there are limits. So yes. Oh, right, yes. It's curious. I'm not entirely sure, what they call scotopic sensitivity or Erlen syndrome. Usually when people are tested for dyslexia, they will test to see if you've got a colour sensitivity. And I've had some years. Now, last year I started off with somebody needing blue, someone needing pink, someone needing yellow, someone needing lilac, and someone needing that green, grass green. That was Kylie, who's gone on to midwifery. It enables I think it's the brain processing the black on another colour. One year I had a student who needed grey, and I could actually understand what she was saying when I said, how does it help you? And she said, on white paper I see the spaces more than the words. But the grey, of course, dulled that out. Now that one I could understand, but it's not the same effect for everybody, but it stops the words moving about. So that is the way the brain processes it. So it's something to do with the way the brain is seeing, you know, black on something. So, yeah, it's a curious, curious thing. Well, well, they will, but it's not that she can't read on white. It's just that and you can also get coloured lenses. Yeah, you can get overlays, plastic overlays. So she may well carry a plastic overlay with her. So you just get the coloured, and they're sort of by prescription. They've got to be a particular colour. But yeah, you just overlay the plastic, and you get the colour. So yeah, it is quite manageable, you know, once it's identified. But I've had people on bright red, bright blue, all sorts, things that I could hardly read off. In fact, I could hardly read off that one last year. But we got there. Right, that's it for now.